Alright, chemistry. So this is the last part of the notes for the year. It's kind of wild. Um, we made it through uh, bonding and solutions and nuclear chemistry and intermolecular forces and all that stuff, which is still up here somewhere, right? I want to do that. All the other notes are still up here, but here we are, right? 97 and 98 acids and bases, and then we have 99 up to 104 organic chemistry. Now, full disclosure, as with many of the topics, in the full disclosure of not having a regents examination to answer to, I will admit that not every part of every topic is particularly interesting, and I am doing what I can to cut out the kind of more boring or more like heavily calculation based, because in my opinion that's like better left for a math class than a science class. This is more about the concepts and the connections than about the math. Sometimes we do have to do the math when we did moles, when we had GFM, ideal gases and the combined gas law. There we needed the math to combine, to piece together the concepts. But here, it's less important, right? Conceptually, acids and bases can be done without a ton of math. Conceptually, organic chemistry can be done with basically no math. That's mostly pictures and reading. But let's talk about acids and bases. We'll move into organic chemistry. There will be a separate video that will go up with any lab work. I think I definitely have one acid-base lab, and I definitely have one organic chemistry lab. The organic chemistry lab might be a demo. Well, not a demo, a virtual lab, because I think I know where a really good online simulation is for organic chemistry. I'll have to double check that. Anyway, acids and bases. Here we go. One of the nicest units that we talk about, not just because it's a short unit, but also because it's like very straightforward. Acids and bases are things that you actually use kind of daily, that you don't think about. Granted, we use kind of weak versions of acids and weak versions of bases, but they're something that's we're kind of this is one of the few topics in chemistry where it's very tangible, and it happens on like a macro level instead of happening on an itty-bitty microscopic level. What are acids? What are bases? What are these things? So we'll talk about basic identification and some definitions here, but acids and bases on their own, they are electrolytes, which we've talked about before. Electrolytes are any substance that will conduct electricity in the liquid phase or when you dissolve them in water. So if you have an acid or you have a base that's dissolved in water, it's going to be an electrolyte. It will conduct electricity in some fashion. When we talked about them before, I said that ionic substances or ionic compounds, depending on how you want to word that, but ionic substances and ionic compounds are also electrolytes. So a very common question that I will ask you, which of the following compounds is an electrolyte? And I'll ask in the context of, really, I'm asking you to identify which of the following compounds is an acid, which of the following compounds is a base. And in order to look at this, we need part of the reference table that we have not looked at yet. Actually, I'm going to pull this part up too, because I don't think I have it on here. I should pull this up. I should pull a lot of things up. I'm trying to think if I need... No, I shouldn't need the actual periodic table. You might want to grab your the periodic table part of the reference table and keep it handy. But, quick organization. I'm going to put the organic chemistry stuff with the organic chemistry. And I will leave the acids and bases stuff here with the acids and bases. Lovely. Okay. So, on your reference table, down here on page 6, I have two tables, table K and table L. It's a list of common acids and a list of common bases. And if you find the question, which of the following is an electrolyte, these two tables are the first place you should look, because all acids are electrolytes, all bases are electrolytes. So you should look for one of these formulas here, or one of these formulas here. Now, I'm going to stick on this list for just a second here, just to identify it. Like, there are acids here that are common that you would recognize. The bases are less common, but there's one that you should recognize. But here, hydrochloric acid, you should recognize. That's your stomach acid. That's the only place you would really commonly use it. But we call these common acids because they're used a little more frequently. Nitric acid is something that might show up in acid rain. So if you remember talking about acid rain in your living environment class, so biology, maybe in 7th grade science, acid rain is usually sometimes nitric acid. Other times it's sulfuric acid. Kind of depends on the content of or the geography of the area where that acid rain is happening. Carbonic acid is something that many of you are keenly familiar with. Carbonic acid, if you look, is H2CO3 or CO2 aqueous. This is the carbonation in a soda or in a soft drink, right? So like Coca-Cola is a carbonated beverage because it has carbonic acid, and this is why dentists, medical professionals will typically tell you don't drink too much soda, or don't drink it every day, don't drink it all the time. And the reason for that, one, super sugary, right? So you have lots of that going in your body, which your body doesn't always need and process. But also, it is acidic. It has carbonic acid in it, and that acid will start to eat away at your teeth, right? It can affect your throat, and consuming excess acid can contribute additional acid to your stomach, which generally is not good news. Can help to contribute a diet that's high in kind of like excess acid intake can contribute. I shouldn't say lead. Can contribute, is a contributing factor, could be a contributing factor to like acid reflux. If anyone has acid reflux, it's very uncomfortable. It's kind of what it sounds like. It's the acid in your stomach that's supposed to stay in there. It comes up through your esophagus, through your throat, and it feels like you are burning because, again, it's an acid. So carbonic acid is the acid in soda. Ethanoic acid, one which is also called acetic acid, has this funny formula. It could be written in two different ways. Both of these, you should notice, can be written in two different ways. Acetic acid is commonly used when cooking. It is vinegar. So vinegar is actually an acid. And again, this is like vinegar has a particular taste, it has a particular smell that is actually fairly common amongst acids. Now, vinegar being acidic, truth be told, carbonic acid and acetic acid, so the carbonation in soda and the acid that is the active ingredient or the key in vinegar, they're not particularly strong acids, which is why we are able to consume them. And why they don't eat through our organs, and they don't mess up your your pots and pans or your glasses too much. They're fairly weak acids. However, in large doses, right, they can still be a force here. But yeah, generally acids are kind of sour, bases are kind of bitter. Bases can be all slippery to the touch. I said there weren't a lot of common bases that you might recognize, right? Sodium, potassium, calcium hydroxides you probably don't recognize, but aqueous ammonia. Ammonia is kind of like a name of a chemical that you might be familiar with. It's found in cleaning supplies. There are ammonia-based cleaners and ammonia-based cleaning solvents, and it, again, has a fairly particular smell. There are other bases that are used in soaps. I want you to think about what I just described as far as bases. They're bitter and slippery to the touch. Soap. Soap is bitter. If you've ever eaten it or gotten it in your mouth, I don't know why you would eat soap, but live your life, I guess. Slippery to the touch. That's a base. Again, a weak base, because if it was a strong base, it would start to react very, 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 I don't want to say, I wish it was better with words. I'm just going to say strongly. It's not the word I'm looking for, but it would react strongly. But yeah, the things that we'll use commonly are weak versions of acid, weak versions of bases. Both acids and bases can cause color changes in solutions called indicators, and I'll get to indicators in a moment. They're also on the reference table. If you stuck on page 6 and you looked in that bottom left corner, you would see a list of indicators, which I will talk about on the next page. Acids will react with active metals to liberate gas, and anything above hydrogen on table J will react with an acid to form hydrogen. Anything above hydrogen on table J. Now, table J is something that maybe you remember, maybe you are a little bit like, I remember table J. So here's table J. It's the activity series, all right? The key is activity. If you see that something is reacting, you should look here at the activity series. Notice that hydrogen is way down here towards the bottom. All right, so if we're talking about metals that are more active than hydrogen, we're talking about most of the metals here. The only ones that are not more active than hydrogen are below it. It's copper, silver, and gold. They're actually fairly inactive. They're fairly inert metals. They don't like to do things. All the other metals, pretty strong, pretty active. They will react with acid to release gas. Very common reaction. Now, how do we define what is an acid? How do we define what is a base? These definitions, these two definitions, the Arrhenius definition, Bronsted-Lowry, the actual name, these names, not super important. The important thing is to remember the bullet point descriptions of what is an acid and what is a base. According to the first definition, acids are any substance that releases H+ in aqueous solution. Now you might see the word release, you might see the word produces, you might see the word yields. They all mean the same thing in this context. So which of the following chemicals or which of the following substances releases, which of the following substances produces, which of the following substances yields H+. If it produces H+, if it makes H+, when you mix it with water, it is an acid. It counts as an acid. A base, in the same definition, is something that releases or produces or yields OH-, right? So if I'm looking, I want you to notice something. I'm going to look back at the common acids and look back at the common bases. If we look at the acids, look at all of these. H, 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 H. They all of them have this leading H. Well, they lead with H, and if you remember, when we're making a chemical formula and we're looking at it in terms of charges or apparent charge, if it came first, it was positive. So there it is. That H, that leading H, is a positive H. When you dissolve it in water, it splits into that H+. There it is. That's what defines it as an acid. The bases down below, now 3 out of 4 isn't bad. But look, there's that OH, OH, OH. All of them have that OH at the end. When we're talking about charge, when we're talking about forming compounds, if it was at the end, it meant that it was a negative. So the OH at the end is an OH negative. That's what it produces. That's how we can define them as bases. That's our first definition, first version of how do I define an acid, how do I define a base, what does it produce in water? The second version is what does it do with protons, or what does it do with H+. H+ is a proton, just for reference, all right? Any species, all right, I want you to do something here. If you see the word species, replace it with the word substance. So when you read the word species, I need you to think substance. Any substance that can donate a proton to another substance is considered an acid. So it is a proton donor. It's able to give them away. Here is a proton, enjoy it. Right? Bases are the opposite. Rather than donating a proton, they will accept it. So they take it in. All right. Again, you do not need to remember the names of the definitions, but you do need to remember what the definitions say about an acid or what they say about a base. last thing on this page is neutralization, and this is something that we take particular interest in because we don't always want acids to be acidic, we don't always want bases to be basic. Sometimes we need a neutralization. Now, neutralization reactions occur between strong acids and strong bases. There's a small distinction there. If the acid and base are not strong, you're not going to get a neutralization, or at least not a full one. If you have a strong acid and a weak base, you're still going to end up with mostly acid. If you have a weak acid and a strong base, you still end up with mostly base. If you have a weak acid and a weak base, you're going to get a little combination of like, it's kind of acidic, it's kind of basic, it's mostly just like very annoying because this is not doing what I want it to do. Neutralization is a strong acid and a strong base. And it will always result in the formation of exactly two things. It will result in the formation of a salt and water. Now, when I say salt, right, not necessarily table salt, it will always result in the formation of an ionic compound, which means metal and nonmetal, right? Remember, definitions for ionic stuff. The example is NaOH. I'm just going to underline this OH and this H here, right? This OH and this H, they combine to form H2O. And then if you look, this Na and this Cl, well, they combine to form NaCl. When you have a neutralization, it's typically between a strong acid and a strong, well, it has to be between a strong acid and a strong base. There's an OH minus, there's an H plus, they smash together to form water, H2O. The other parts of the acid and the base also smash together to form the salt. All right. Now, I'm not super concerned about this bullet point here. However, this is, I made this note just now, I wrote it in, but I'm reminding you, I'm drawing attention to it. The definition for a salt is it's an ionic compound, metal and a nonmetal. It's not an acid, it's not a base, it's neutral. Right, that's why we call it a neutralization. Sorry, thirsty. It's super warm everywhere. Please stay hydrated. Alright, I got iced tea. Alright, moving right along. We'll keep going. The strength of an acid or the strength of a base, you might be wondering, like, how the heck am I supposed to tell if this acid is strong or not? Well, there are two very simple rules. There's one rule for acids and there's one rule for bases. And if you keep track of those rules, you will know, okay, this is strong or this is weak. So the rule for acids is it organic or inorganic? Right? Inorganic acids are acids that do not contain carbon. They are strong. So acids with no carbon, if we look at our, hello? Oh gosh, there we go. If we look at our list of acids here, look, this is no carbon, no carbon, no carbon. In fact, these top ones all do not have carbon, they're all strong. The two that I said earlier were weak, carbonic acid and acetic acid, so carbonation in sodas and vinegar. Look, they both have carbon in them. That's why they're defined as weak acids. Right? So inorganic, strong. Organic acids are things that contain carbon. They are weak acids. They will also be weak electrolytes. They don't conduct electricity very well. And the reason for that is, goes hand in hand with why they are weak acids. The reason they're weak acids is because they don't produce a ton of ions. They don't produce a ton of, of H pluses, right? Definition for an acid was it produces H plus when you put it into water, or it donates H plus. Organic acids are not very good at giving away that H plus, and as a result, they're not very good acids. The rule for acids, organic or not. Organic weak, not organic strong. The rule for bases, is it a metal hydroxide? Metal hydroxides are things that contain a metal, something on the left side of the periodic table, and hydroxide, which is this OH group. So, if we look, right, 3 of our bases here are metal and hydroxide. They are strong. anything else is a weak base. Remember, I said ammonia was a weak base. It has neither a metal, nor does it have that OH group, which is why it's considered a weak base. That's the rule for bases. Is it a metal hydroxide? Yes, strong. No, weak. That's it. That's a version of acid-base strength if you can see the formula. There's also the version of acid-base strength that's based on the pH scale, which you've talked about before. This tells us how acidic or how basic something is. It ranges from 0 to 14. So 0, 1, 2, 3, 6, 7, 8, 9, 10, 11, 12, 13, 14. Here's the pH scale. This is acid. This is base. 7 is neutral. Right? So it's a scale. 0 is super acidic, 14 is very basic. If I go from 7 to 6, I'm becoming more acidic. If I go from 7 to 8, I'm becoming more basic. However, this is the important part. 1 pH unit, so if I change from here to here, right, from 7 to 6, that's a 10 times change, which means something with a pH of 6 is 10 times more acidic than something with a pH of 7. Right? If I go from 6 to 5, that's another 10 times. If I were to skip straight from 7 to 5, that's 100 times, because it's 10 times 10. Every time I move by 1 on the pH scale, it's actually 10 times stronger. Right? And this is why we try not to mess with stuff that's down on the 0, 1, 2 end of the scale. That's why we don't mess with stuff that's on the 12, 13, 14 end of the scale. Because that's really strong. That's very acidic or very basic, right? Hundreds of thousands of times stronger than neutral. Generally bad news for people. Alright, the pH scale, right? The last thing that I'm going to talk about with acids and bases is this indicators. I'm not fussed over titration. Titration is just neutralization. If you know neutralization, that's what titration is. But indicators are special chemicals that change color if the pH changes. They have very specific pH ranges and color changes. And there's a number of them here on table M, which we're going to look at right now. So table M is here hanging out as common acid-base indicators, and I'm going to do an example right here with methyl orange right now. Right? Methyl orange has a pH range from 3.1 to 4.4, and it changes color from red to yellow as it changes, as it goes from 3.1 to 4.4. What this means is that at 3.1, its color is red. At 4.4, its color is yellow. If we're in between those, we get a color that's in between red and yellow. Well, if I combine red and yellow, I get orange. Right? So if I have something, let's say, for the sake of argument, right, my cup is filled with something that has a pH of 3.1 exactly, and I drop some methyl orange in it, and I look, it's going to be red. Right? If I have my mug, and there's something with a pH of 4.4 in here, and I drop some methyl orange in it, and I look again, it would be yellow. If I had something with a pH of like 3.8 and I look, I wouldn't see red, I wouldn't see yellow, I would see some shade of orange. The funny thing is if I had something in here with a pH of 2, right, 2 is below 3.1, but the color is red, orange, or yellow. Those are the only options. If it's red at 3.1, it's still red at 2. So if my solution, if my acid in here has a pH of 2 and I drop methyl orange in and I look, it's still going to be red. If I had a pH of 1, drop methyl orange in, it's still going to be red. If I had a pH of 6 and I drop methyl orange in, it would be yellow. If I had a pH of 11, I drop methyl orange in, it'd be yellow. Anything below that left number is going to be that left color. Anything above the right number is going to be the right color. When I'm talking about sides here, right? I'm talking about sides there. Anything in between is going to be whatever a mixture of those two colors is. But I can use these indicators to identify between different things. So if I look here, solution A has a pH of 2, solution B has a pH of 5. I can actually use methyl orange to distinguish that, because if I drop it into the 2, methyl orange will very clearly be red. If I drop it in the 5, methyl orange will very clearly be yellow. I could not use the next one down. I could not use bromthymol blue, because if you look, see at 6, it's yellow, and at 7.6, it's blue. Well, if I drop bromthymol blue in something that has a pH of 2, it's going to be yellow. And if I drop it in something with a pH of 5, it's still going to be yellow. So bromthymol blue does not work. Right? I can do that with either of these other ones. If I look at, I'm going to look at number 3 here. Solution A has a pH of 7, solution B has a pH of 10. I cannot use methyl orange because 7 and 10 are both on this side. So they're both going to be yellow. I maybe could use bromthymol blue because 7 is within the range, so I'd see green, and 10 is outside the range, so I'd definitely see blue. I could use phenolphthalein, that's how you say this one, because on the 7 side, I'd be over here, it would be colorless, and on the 10 side, I'd be over here, it'd be pink. I could probably use litmus. At 7, it would be kind of purple-ish, but at 10, it would very clearly be blue. I would not be able to use bromcresol green, because both of them would be blue. I could probably use thymol blue, because on the 7, it would be yellow, and on 10, it would be blue, right? But that's how that's how you would look at indicators, and that's how you would be presented with indicators. Right? It's a process. Now, that is kind of it for acids and bases. There's going to be a lab. It's very likely there's going to be an acids bases quiz next Tuesday. I think Tuesday. Monday would be a review day. Yeah, I think I like Tuesday there. So if you have questions, please find me, email me, send me a pigeon or something, right? I'm going to, as quickly but also thoroughly as I can, just talk about the organic chemistry basics that I would like you to be familiar with. Now, organic chemistry is a strange and kind of scary class. When it's on its own, we're really just going to touch the surface of what is organic chemistry, what does this mean, right? The reason organic chemistry is a kind of scary class on its own is because organic compounds have a ton of their own rules. They act uniquely from other compounds that are inorganic, and you really have to know them front ways, back ways, upside down, left, right, inside out. And it's kind of wild. I took 2 semesters of organic chemistry in college, and I still feel like there are many things that I just barely understood. I understood just enough to get by. But again, we're just touching the surface of what organic chemistry is. On its most basic level, organic chemistry is the study of carbon and its compounds. Life on Earth is based on carbon-based stuff, right? Living things have carbon in them. That's an essential piece of their makeup. Carbon is a super weird element because it's capable of covalently bonding to other carbons almost infinitely. it says infinite, and like I guess it's functionally infinite because we've never really scraped how long of a chain of carbons we can make. But the fact that carbon has 4 bonding sites, right? When we talked about carbon, we made a Lewis diagram. There were four dots because there are 4 points around it, which means that I can attach here or here or here or here, really and that causes some like wild and unique properties. Carbon covalently bonds to other carbon in 3 ways. It does so in chains, rings, and networks, right? And what that means, if it's in chains, then what you would see is you would see something like that, right? A ring of carbons is quite literal, right? And really there are other things going on here. Just the same, there are also other things going on here because they will always have 4 bonding sites. Network. A network is something like diamond or graphite or coal, where you have these like layers of carbon that are just attached to the next layer that are attached to the next layer. But chains, rings, and networks, if you see that phrasing or you see those properties like what element bonds to elements in chains or rings or networks, it's carbon. We're talking about organic chemistry, right? Now, there are some basic properties of organic compounds. I'm going to give you like the highlights. This is like the biggest defining feature of most organic compounds, and that one that I just circled, little or no polarity in the bond, really leads to all of the other ones. The fact that it has no polarity means that it is soluble in nonpolar things. It has no polarity, so it will not conduct electricity because it's not positive negative. There's nowhere for charges to go. Because it has no polarity, or little polarity, there's no negative positive side, they're not attracted to each other, so the boiling and melting points are low, because it's fairly easy to pull them apart. They don't have that strong intermolecular force of attraction. Because there's little or no polarity, when they bump into stuff, they don't have a really good reason to bump into stuff. They don't have a reason to be attracted to or repelled from things, so they're going to react more slowly. The biggest one to remember for organic compounds is that they have little or no polarity, and that gives you kind of all of the other pieces. You have to think about it. You have to work your way through it, but that's what the bond types. That's the important part, right? Now, I'm going to talk about hydrocarbons, which are alkanes, alkenes, and alkynes. Talk a little bit here about isomers. The naming conventions are things that I'm going to do in a lab. So I'm gonna save the naming conventions, which is actually those 2 pages there, 101 and 102. And then I'm gonna skip. I'm actually gonna go. What I'm gonna talk about today are hydrocarbons, alkanes, alkenes, and alkynes. And then I'm gonna skip down here to functional groups and the types of organic reactions. That's where we'll call it for the notes for now. Again, there'll be a separate video for the labs because specifically for the acid-base lab, because I do need to do stuff at school. But hydrocarbons. Now, scientists, I've been saying this all year, scientists are not like superbly clever when they come up with their names for these things. So, sorry, got some stuff that's like falling over here. Please don't fall over. Okay. Hydrocarbons are organic compounds consisting of hydrogen and carbon. And only hydrogen and carbon, we call them hydrocarbons. These are the simplest organic compounds there are, and they're obtained by refining petroleum. Now, petroleum, raw petroleum, is oil. Oil is a hydrocarbon. Now, hydrocarbons are separated into special families that we call homologous series, which is, they're on table Q. We'll talk about that in a moment. It's one of the pages that I pulled from the reference table. Each member of a homologous series differs from the next by a single carbon. Right. Now, the hydrocarbons, the three classifications, the three families of hydrocarbons are called the three homologous series. And I'm just going to quickly point something out. I'm going to look at table Q, which should be this way somewhere. Maybe? Is it down? Just kidding, it's down. Here it is. The homologous series of hydrocarbons are alkanes, alkenes, and alkynes. Right? There are general formulas here. I'm not super concerned about those. You will be able to identify the structure for an alkane, structure for an alkene, structure for an alkyne. And I'm going to do those now. Right, so alkanes. Alkanes are hydrocarbons, hydrogen and carbon, that contain only single bonds between carbon atoms. Only single bonds. So if you're looking at the structure and you only see single lines in between the carbon atoms, then you have an alkane. They are considered to be saturated. And this is the second time we've seen this word saturated. We talked about solutions being saturated, they're completely full. Alkanes are saturated because they contain all single bonds, and every carbon is attached to 4 separate atoms. So if you have a single carbon, if all of them are single bonds, that's an alkane, only single bonds. The names of alkanes will always end in A-N-E. There's going to be a pattern that you will recognize in just a moment. So alkanes, single bond, saturated, end with A-N-E. Here comes the pattern. Alkenes. These are hydrocarbons that contain at least one double bond. Single to double. Alkenes are considered to be unsaturated. And the reason for that is because you could add more stuff to an alkene. Because you have a double bond, it means that 2 carbons are being kind of like selfish with each other. They could connect to more things, but they're deciding to make the bond between them stronger. Remember, double bonds are stronger than single bonds. Alkenes will always end in E-N-E. They'll end in ene. Now, if you're clever, you've already figured out the pattern. Alkynes. Single, double. Alkynes are going to have at least one triple bond. They are also unsaturated, and their names will always end in -ine, Y-N-E. The nice thing about alkanes, alkenes, and alkynes, they go in alphabetical order. A-N-E, E-N-E, Y-N-E. They go 1, 2, 3, saturated, and unsaturated, and unsaturated. Right? Oh, I forgot that isomers was on this. Okay. Very quickly, isomers. Last time we had iso in front of something was isotopes. Isotopes were same element, different neutrons. Isomers are substances. So these are compounds. Substances that have the same chemical formula, but different structures, are called isomers. They're made up of the same number and types of atoms, but they are put together differently. When that happens, right, each of these is 1, 2, 3, 4, 5 carbons, right? I can underline each of the carbons in each of these. 2, 3, 4, 5. And if you were to count, there would be 3, 6, 12. There are 12 hydrogens on each of them, and you can count. I'll leave that as an exercise for you. Each of them has 5 carbons, each of them has 12 hydrogens, but they're all put together differently. Because they are put together differently, they will differ from each other in both physical and chemical properties because they have different structures. And this is something that I have mentioned time and time again. Different structures means different properties, but now we have like a special name for them. Isomers. Same chemical formula, so same makeup, but different structures, so put together differently. You can make, 16, 20, a bajillion different things out of the same Lego pieces, but if you piece them together differently, they will act differently, they will move differently, they will react differently. So same thing here, right? Now the naming system, again, that is something that I will address at a later time, if I address it at all. Full disclosure, I may decide not to do that lab because it's, the naming process is fine, but tedious. All right, now functional groups. I like to look at functional groups as, where's Waldo? And what I mean by that is hydrocarbons are the baseline for everything. But organic compounds get more complicated than hydrocarbons by adding what we call functional groups. They are groups with specific functions, hence functional groups. Now, if you have these organic compounds where some of the hydrogens in a hydrocarbon are replaced by other atoms, which, by the way, are called functional groups, functional groups will give the compounds their distinctive physical and chemical properties. So a different functional group on a similar organic compound, on two similar organic compounds, will they will draw different physical and chemical properties because they are put together differently. Compounds with functional groups will derive their name from the hydrocarbon with the corresponding number of carbons, which again I'll talk about more. So I guess I will. I'll have to talk about naming. Now table R gives you the functional groups. I said that functional groups are like Where's Waldo? And what I mean by that is here are the functional groups and here are their names. So alcohol, ether, aldehyde, ketone, organic acid, ester, amine, amide, and the halides, right? These are the different functional groups. What I mean by Where's Waldo, right? Here is an organic compound. Right. It's not a hydrocarbon because it's not only hydrogens and carbons. If I had to identify what is the functional group on this, find the thing that isn't carbon and play Where's Waldo. Where is Cl on my big list? Well, here it is. So that means that this is a halide. Again, if I made a different organic compound, well, what we need to do is find where is the weird thing. Okay. And this is where to be careful. See that, so I'm going to identify that is the weird thing. All right, so let me find that. Oh, well, here it is. That means that this is an aldehyde, right? Some of these you will recognize. Alcohol is obviously alcohol. Aldehyde. If you have heard of formaldehyde, that is an aldehyde. Has a very specific smell. Nail polish remover contains acetone. Well, that is a ketone. Has a different functional group. Carbonic acid and acetic acid are organic acids, right? If you remember talking about amino acids, amino acids are like building blocks of DNA, right? They are amines. It's a combination of an amine and an organic acid. Esters are considered aromatics, which is something that has a nice smell to it. But yeah, so each of these has their own specific function. They do different things. And when I say that they are commonly Where's Waldo, you need to identify what is the functional group, find the weird thing, match it to table R, play Where's Waldo, and you'll have your answer there. The very last thing I'll talk about here are the types of organic reactions. They are specific to organic. They have to happen with compounds that have carbon in them. Substitution reactions are exactly what they sound like. Substitution is a replacement. It has to be a saturated hydrocarbon, which means it's all single bonds. Substitution has to happen with single bonds, which means that it will only ever involve alkanes. So substitution will only ever involve alkanes. Addition means that we're adding to something. We're adding them at a double or a triple bond, which means that it will involve alkenes or alkynes. Remember, they were unsaturated, so addition has to be unsaturated things. We can add to them because they are not full yet. Because they are unsaturated, we can add to them. If they are saturated, we can only substitute. Combustion is everyone's favorite. Burning stuff. Fire. Fire is combustion. It's an organic reaction. The products of complete combustion are CO2 and H2O, carbon dioxide and water vapor. This would be like wonderful, lovely, perfect combustion. CO2 and H2O. Incomplete combustion happens more frequently. It's carbon monoxide and water vapor. Most commonly, you have a combination of the two. The more incomplete the combustion, the more wasted material you have. Traditional wood fires are actually poor combustion. So those reds and those yellows, that glow that you get from a nice wood fire or a bonfire, is actually like the product of an incomplete combustion. Complete combustion, much more common with like a gas stove. That blue-white flame is a nice, lovely, complete combustion. But combustion is burning, and you will always produce water vapor, and you'll either make carbon dioxide for complete or carbon monoxide for incomplete. Right. Now, esterification. And with the organic reactions, most commonly it's an identification, it's a definition. So these are all typically definitions. Esterification is a reaction between an acid and an alcohol that produces ester in water. Something terrible that either last year's class or the year before came up with. Again, trying to remember that like acid and alcohol makes an ester. My Aunt Esther was an awful influence. She was always on acid and alcohol. I don't have an Aunt Esther, but just like it was a way for them to remember the association. Acid plus alcohol makes ester. Aunt Esther was a bad influence because she was always on acid and alcohol. It's a mnemonic to try to help remember it. Just definitions. When I ask you about esterification, it will be what do you need to combine in order to create an ester, or when you combine an acid and an alcohol, what will you produce? You'll produce an ester. Right. Saponification. Saponification, I can tell you, if I ask you, it will be that saponification is the production of soap. It is the reaction between an ester and an inorganic base. Let me make sure I got that right. I did not get that right. I apologize. No, it is gonna be. Triglyceride. Why do I feel like it's not totally right? No. Ester or ether? Oh, he's an ether. This is how long. No. It's an ester and a I'm sorry. Ester and an inorganic base, but the reason I don't even remember the reactants is because saponification is always about the products. Saponification makes soap. And then fermentation is actually one that usually people recognize fairly easily. When you ferment something, you take sugar and you break it down into carbon dioxide and alcohol. This is how we produce alcohol. You ferment. Right? The last organic reaction that we have here is polymerization. And polymerization just means to take lots of small pieces called monomers and connect them to each other to make a polymer. Poly, like more than one. So monomers join together to make polymers. Right? I will tell you that, like, when I ask you about them, I'll probably ask a fermentation question. I'll probably ask an esterification question. It's fairly rare that I ask about saponification. Anyway, these are our basic types of organic reactions. When I do naming, I will talk about these organic prefixes. But that will be either a simulation or a demo. Again, separate video for the lab. But that's it. That's the notes. That's chemistry. Or, you know, the surface of chemistry. Next video you'll see is labs, and then it's just review. We don't have very much school year left, so I'll make sure y'all are prepped for the final, and junior year will be complete. Until next time, chemistry, I will see y'all. Be good, be safe, and take care until then.